Welcome back to another video. In this video, we'll continue to look at 17b, rules for differentiation. So we know that we can easily find the gradient of a linear function by using the formula rise over run. This is essentially the change in y values, so the vertical values, over change in x values, the horizontal values. We use the Greek letter delta, so this little triangle, to denote change. When we know the two coordinates, we can simply plug them into the formula y2 minus y1 over x2 minus x1 to find the gradient. And we already know this. When it comes to a curve, once we know what the derivative function is, then we can sub in the x value, and note we use the x value only to find the gradient of this tangent line. Think back to when we did rate of change. This is essentially the instantaneous rate of change, or the instantaneous gradient at this particular point. So f prime of x is known as the Lagrange's notation with a prime mark. Another way is that you can write y representing the function and just write y prime. So they both represent the derivative function of f of x. So they're two commonly used notations when denoting the derivative of a function. The Lagrange's notation, f prime of x, the one we just looked at, and dy over dx. So dy over dx is known as the Leibniz notation. And now let's say if we have a function y is equal to x cubed, then the derivative can be denoted by dy over dx. So we can write dy over dx is equal to 3x squared. And in general, we say that if y is a function of x, then the derivative of y with respect to x is denoted by dy over dx. Okay, so note that it doesn't have to be dy over dx all the time. So in fact, for example, for a position versus time function, we would have x is equal to t something, and in that case, our derivative function will become dx over dt. And as you can see, similarly, if z is a function of t, then the derivative of z with respect to t is denoted by dz over dt. Okay, so here's an example. In question A, you can see that we're finding the derivative of y with respect to t. So if y is equal to t squared, then dy over dt, so the derivative of y with respect to t is equal to, so you bring the 2 to the front and you reduce the power by 1. dy over dt is simply 2t. Okay, question B, we have x is equal to t cubed plus t. And we're finding the derivative of x with respect to t. So dx over dt, we're going to differentiate this function. So we take the 3, bring it to the front, reduce the power by 1, so 3 minus 1 equals 2, and then for the second term t, it simply becomes 1. So we say that the derivative of x with respect to t is 3t squared plus 1. The last question, we have z is equal to 3rd x cubed plus x squared, and we want to find dz over dx. So we want to find the derivative of z with respect to x. Okay, so we bring down the power to multiply with the third, and then we reduce the power by 1. So 3 minus 1 equals 2. The second term we have, so we bring the 2 to the front, and the power becomes 2 minus 1, which is 1. Okay, so 3 times 3 equals 1, and dz over dx becomes x squared plus 2x. So we say that the derivative of z with respect to x is x squared plus 2x. So here is essentially finding the derivative of these functions. All right, and in this example, we're basically doing the same thing, finding the derivatives. But as you can see, the questions are getting trickier. So we need to expand the brackets, or we need to simplify before we can find the derivatives. So in question A, we have y is equal to x plus 3 squared, and we want to find dy over dx, which is the derivative of y with respect to x. So let's expand the bracket first. So expanding this perfect square, we have x squared plus 2 times x times 3 equals 6x plus 3 squared, which is 9. Now, if we differentiate this, dy over dx, so we bring the 2 to the front, reduce the power by 1, the first term becomes 2x, The second term, it's simply 6, and the constant term 9 is gone. So the derivative of y with respect to x is 2x plus 6 in this case. Second question, we have z is equal to 2t minus 1 squared times t plus 2, and we want to find dz over dt. So the derivative of z with respect to t. Now we have two brackets, and the first bracket is a perfect square. So let's expand the perfect square first. So it's 2t squared, which is 4t squared, minus 2 times 2t times negative 1, which is negative 4t, and plus negative 1 squared, which is positive 1. And let's keep the second bracket there. Okay, so now let's expand the brackets again. And using distributive method, we need to make sure that every single term in the first bracket, they need to multiply with every single term in the second bracket. So 4t squared times t becomes 4t cubed. And then 4t squared times 2 equals 8t squared. Okay, the second term, negative 4t times t equals negative 4t squared, and negative 4t times positive 2 equals negative 8t. And last term, so 1 times t equals t, and 1 times 2 equals 2. Now let's try simplify by collecting like terms. We have a 4t cubed, and we have 2t squared, so 8t squared minus 4t squared, we have 4t squared left. We have negative 8t and 1 positive t, which becomes negative 7t. We also have the plus 2 in the end. And now let's find dz over dt. So differentiate the first term. We bring the 3 to the front to multiply with the 4. 3 times 4 equals 12, and we reduce the power by 1. We bring the 2 to the front to multiply with the 4, becomes 8, and reduce the power by 1. And minus 7t becomes minus 7. The constant term 2 is gone. So dz over dt, the derivative of z with respect to t, is equal to 12t squared plus 8t minus 7. Okay, now question C is y is equal to x squared plus 3x over x. And we want to find the derivative of y with respect to x. So we can simplify this expression because x is a common factor. So if we divide x to the bottom, we have 1 left. And if we divide x to the top, we have x plus 3 only. So the original function can be rewritten as x plus 3 over 1, or simply x plus 3. And finally, dy over dx is simply 1, because the constant term 3 is gone. Okay, last question. Differentiate y is equal to 2x cubed minus 1 with respect to x. So here it's essentially saying that we need to find dy over dx. And we know that we simply bring the power to the front to multiply with the 2, becomes 6x to the power 3 minus 1, which is 2. And then the constant term, negative 1, is gone. So the derivative of y with respect to x is 6x squared. Okay, now we're looking at operator notation. So operator notation is that the operator gives you the derivative. So let's say if we want to find the derivative of 2x squared minus 4x with respect to x. So this can also be written as d over dx. So we're basically trying to find the derivative of this function. So as you can see, although we have different notations, we're basically finding the same thing. So question A, d over dx. Okay, 5x minus 4x cubed. So we want to find the derivative of this function. So 5x becomes 5, and we bring down the 3 to multiply with the 4, becomes 12, and x to the power of 3 minus 1, which becomes 2. So we say that the derivative of 5x minus 4x cubed with respect to x is 5 minus 12x squared. Question B, we want to find d over dz, and the function given is 5z squared minus 4z. Again, let's just differentiate. So we take the 2 to the front to multiply with the 5, we have 10 z to the power of 2 minus 1, which is 1. And minus 4z becomes minus 4. So we say that the derivative of 5z squared minus 4z with respect to z is 10z minus 4. Okay, lucky last one. We want to find d over dz and 6z cubed minus 4z squared. Again, we want to find the derivative of this function with respect to z. So we bring down the power 3 to multiply with the 6, we have 18, and reduce the power by 1, we have z squared. Second term, so negative 4 times 2 becomes negative 8, and reducing the power by 1, we have z to the power of 1. And we say that the derivative of this function with respect to z is 18z squared minus 8z. Okay, last example. For each of the following curves, find the coordinates of the points on the curve at which the gradient of the tangent line at that point has the given value. So first thing first, tangent implies that we need to find the derivative function. For example, in question A, when the gradient is equal to 8, what are the x values? In other words, at what values of x does the gradient equal to 8? We know the function is y is equal to x cubed. We know the gradient is equal to 8. So once we find the x values, we're going to sub them back into the original function to find the corresponding y values. And finally, we pull them into the coordinate forms. So in question A, okay, y is equal to x cubed. This implies our derivative function dy over dx is equal to 3x squared. And since the gradient is 8, we're going to set this derivative function to be 8. Now we have 8 is equal to 3x squared, and we're going to solve for the x values. If we divide 3 to both sides, on the left-hand side we have 8 over 3, and on the right-hand side we have x squared. And solving for x, we're going to take the square root, and keep in mind we need to take both the positive and negative values when taking the square root. So we have x is equal to plus or minus square root 8 over 3, which is equal to plus or minus 2 and square root 6 over 3. Now, let me continue up here. Once you find the x values, we're going to sub them back into the original function to find the corresponding y values. So when x is equal to 2 square root 6 over 3, my corresponding y value is equal to 16 square root 6 over 9. When my x value is equal to negative 2 square root 6 over 3, the corresponding y value is equal to negative 16 square root 6 over 9. Now I have my two coordinates. I can put them into coordinate forms. So we say that at these 2 points on our curve, the gradient is equal to 8. So what about question B? We have y is equal to x squared minus 4x plus 2, and the gradient is equal to 0. Okay, let's find the derivative first. dy over dx is 2x to the power of 2 minus 1, which is 1, and minus 4. The constant term 2 is gone. And we know the gradient is equal to 0, so we set dy over dx to be 0. So 2x minus 4 is equal to 0, and we solve for x values. So if we plus 4 on both sides, so now we have 2x is equal to 4, and if we divide 2 on both sides, we can easily find what x is. So x is 2. Okay, and note in this case we only have one x value. And once we know this x value, we're going to sub this back into the original equation. So when x is equal to, not 6, when x is equal to 2, what's the corresponding y value? Okay, so we have 2 squared minus 4 times 2 plus 2. The corresponding y value is negative 2. And therefore we say that at this point, 2 comma negative 2, the gradient is equal to 0. Last question, we have y is equal to 4 minus x cubed. dy over dx, the constant term 4 disappears, and the second term, negative x cubed, becomes negative 3x squared. Okay, now we have the gradient, negative 6, is equal to our derivative function. So if we divide negative 1 on both sides, we are left with positive 6 is equal to 3x squared. Okay, so we're trying to make them positive numbers, be positive. And if we divide 3 on both sides, we have 2. And on the right hand side, we're left with x squared only. Taking the square root, x is equal to plus or minus square root 2. Finally, if we sum these two x values into our original function, when x is square root 2, so when x is positive square root 2, the corresponding y value is 4 minus 2 to the power of 3 over 2. And when x is negative square root 2, the corresponding y value is 4 plus 2 to the power of 3 over 2. So at these 2 points on our curve, the gradient is equal to -6. So I hope you find this video helpful, and I'll see you in the next video. Bye!